Hey, we're continuing on here where we left off, chapter 4. We wrap it up and then move on. So here last time in chapter 4, we were talking about the atom. We also got into the important sort of experiments that led to the modern understanding of the atom. Remember that the atom is mostly empty space. It has a very dense positive core, which is the nucleus. Inside the nucleus, we have our protons and our neutrons flying out about the nucleus at some distance and moving around are our negatively charged electrons. Remember that most of the mass of the atom is made up of that nucleus, as both protons and neutrons are about 1,800 or so times heavier than an electron, with the neutron, as we talked about, being just slightly the heaviest out of those three. We also got into atomic number, which is the number of protons there are. Remember, the atomic number can be found above the symbol on the periodic table. So that will tell you the number of protons. Also remember that if it is neutral, it would also tell you the number of electrons that should be there as well, as they should be the same. We also talked about mass numbers. Is the number of protons plus the number of neutrons. The mass number, remember, is not found on the periodic table. So the mass number is not the number underneath the symbol. You do need to calculate that based off of the information given to you. When you do calculate mass number, atomic number, number of protons, electrons, and neutrons, they all should be positive whole numbers. So if you look on the periodic table, the number underneath the symbol, which is actually the atomic mass, pretty much none of them are whole numbers. They're all decimal type numbers. So that's a good way to sort of remember that. The importance of both of these numbers are basically if you take the mass number minus the atomic number, those guys will cancel and that will get you the number of neutrons there are. So if you take the mass number minus the atomic number, we'll get you the number of neutrons. We do write these and we sometimes see isotopes, as we also talked about. Isotopes, which are the same element, but have different mass. And that basically means that they have different numbers of neutrons. Remember, out of protons, electrons, and neutrons, it is the proton that is the most important because every single element has its own number of protons. So it's really the protons that determine the element that you're dealing with. So isotopes have the same number of protons, but different numbers of neutrons, which again is why they do have different masses. We typically write the symbol like this, where we put the symbol there and the mass number top left, atomic number bottom left. And sometimes isotopes are written like this, where it's sort of the symbol and a dash, and that is the mass number when it is written sort of in that form. Any questions on any of those things we talked about there? All right, so I think this is where we left off, was here where I wrote on everything. So let's do that. So for each of these here, figure out the number of protons, electrons, and neutrons there are in each of these cases. Take a minute or two, see what you come up. Let's take a look and see. So once again, when it is written like this, we have up on top is our mass number. Bottom there is our atomic number. So it is the atomic number. It tells us how many protons there are. So this, which is cobalt, would have 27 protons. It has no charge, and we know that because if it did, it would be written right about there. So we don't see anything. So we can safely assume that it is neutral. And because it has 27 positively charged protons, it then would also need to have 27 matching negatively charged electrons. 27 positives, 27 negatives give you 0 overall charge. And then for our number of neutrons, once again, we take the top number minus the bottom number. So that would be our mass number minus our atomic number, and it looks like 33 there. Any questions on that one there? Rolling to the next one, which is chlorine. Once again, we don't see anything written there, so it's neutral. Looking at the atomic number, which is on the bottom, would be 17 protons. Once again, we will have a matching number of electrons because it is neutral. So it would also be 17. For our neutrons, once again, we'll take our mass number, which in this case is 37 minus 17, gives us 20 there. It's like for our neutrons. Any questions on that one? And lastly, on the bottom there is uranium. Once again, starting with the atomic number, which is 92. That tells us the number of protons. We see again no charge, so once again, easy to figure out, matching number of electrons. And then for our neutrons, we'll take our mass number, which is 238, minus 92, which gives you a lot, 146, I think, in terms of the number of neutrons. Any questions on any of those there? Yes, sir.
I think it's uranium that's been removed of its 235 isotope, so it's just 238. It's also called depleted uranium.
That's very good to
And
know.
it actually has a few uses outside of the nuclear physics industry.
Yeah, and you'll talk more about it when you go to 1B and talk about nuclear chemistry. You'll talk some of those things. Any questions about this specifically here? Okay, let's continue on then. For each of these, let's write the symbol with the mass number and the atomic number here. Okay, let's see how we're doing. So once again, here we want to use the periodic table to help us. So krypton symbol is Kr. And again, if we go to the periodic table, we'll find Kr. The number above it, which will be very important in there, is 36, which is its atomic number, which should go to the bottom left. That's also right, the number of protons, which is good because they do give us the number of neutrons. So we could add those numbers together. 48 plus 36 will equal our number of neutrons. And that looks like 84 there, I think. And that would go up on top. Any questions on that one there? Going to the next one, which is nitrogen. Symbol for nitrogen is N. So once again, we'll use the periodic table to help us. And if we look there, we will see lucky number 7 there, which is its atomic number. That once again will go bottom left. Once again, that also is the number of protons, which we're going to use with the neutrons that it gave us, which means that's actually our mass number there. Sorry about that. Our mass number will equal 6 plus 7, which gives us 13. And that would go up on top. Lastly, here we have iron that has a mass number of 56. And we also want to give the protons, electrons, and neutrons. So iron is Fe. Once again, if we go to periodic table, we will see 26 there above iron. That would be our atomic number. Would go bottom left. In this case, they actually gave us the mass number, which would go up on top, which would be 56. From that information, we know that iron here would have, in terms of protons, 26. Again, it is neutral, so it will have 26 electrons. And our number of neutrons here would be 56 minus 26, which would be 30 in this case. Yeah. Any questions on mass number, atomic number, number of protons, electrons, neutrons? Now, what if something did have a charge? Remember, things with charges are ions. And there's really 2 types of ions. There are cations, which are positively charged, and there are anions, which are negatively charged. So for example, if we took our nitrogen there and we have the same sort of setup, but instead of it being neutral, it had a -3 charge. One thing that we would know for sure is because it is still nitrogen, it still has the same atomic number, which means the number of protons here would be 7. The number of neutrons would still be the same in this example, which would be 13 minus 7, which would be 6. So as we can see here, it is actually the number of electrons that change when something gets a charge. And in this case, the number of electrons would be 10 in this case. So 7 positive charges, 10 negative charges leaves you a -3 left over. And that is basically where the charge comes from. Basically has 3 more electrons than protons. So it is a -3 charge. So whenever you see anybody that's an anion that's negatively charged, it basically means that they have gained electrons. The actual number of the charge is how many electrons they gained from the neutral element. So anions gain electrons. Now, if we took something like iron, like we had down there, that's 5626, and we put a +2 charge. Same sort of reasoning here. This is still the atomic number, which means the number of protons would still be 26 for it. The number of neutrons would be still our 56 minus 26 in this example. Once again, here it is the electrons that change, and actually has a +2 charge. So the positive means that it actually has lost electrons. And the 2 is how many it lost. So it lost 2 electrons from the neutral guy, which means in this case, the number of electrons would be 24. 26 positives, 24 negatives gives you a +2 left over for the charge. And once again, that is where the charge comes from. Any questions on that? So things that are cations, they are made by losing electrons. And it's always the electrons because, as we talked about, it can never be the protons because it will change the element. So because the element doesn't change, it just gains a charge. The protons got to stay the same. So it's just electrons that change. So if you see something with a positive charge, it means it lost electrons. And whatever the number is how many electrons it lost from the neutral guy, which pretty much means you could just look at the atomic number and subtract how many electrons that was. Or if you have a negative guy, you can look at the atomic number and add how many electrons they gained, and that will give you the proper number of electrons. Any questions on how to do it with things with charges? All right, so obviously you need to be able to write the symbols, figure out protons, electrons, neutrons, things that are neutral, things that have charges, mass number, atomic number. Any questions on any of that there? All right, so we talked about isotopes, and again, one of the nice things about isotopes is that they really do sort of perform the same way, regardless of what isotope it is. So some advantages of isotopes are that some of them are radioactive, and if you're doing some type of experiment, or maybe you're interested in what happens, say, with copper along the way, you could use a radioactive version of copper. It will do the same sort of chemistry because pretty much most chemistry is involving the electrons. So it'll work and basically behave like non-radioactive copper, if you will. So just by following something like the radioactivity, you can follow what happens with copper through a pathway. Sure. So let's talk a little bit about the periodic table. Periodic table is right there. It is obviously an arrangement of the elements and gives us good information about the elements. First off, when we talk about on the periodic table, we talk about groups mostly. Not too many people use families anymore, but they used to use families sometimes. But we do talk about groups, and groups are basically go up and down. So columns on the periodic table. Depending on the periodic table, you'll see a lot of different numbering. Sometimes you'll see A numbering, sometimes you see B numbering. Sometimes you'll just see numbering 1 through 18 as well, depending on the periodic table that you're looking at. For the most part, in most chemistry classes that you use what is referred to as the A numbering or the representative numbering. And that is group 1 right here, group 2, group 3, group 4, group 5, group 6, group 7, and group 8 over there. So that is the numbering that we use for the periodic table. We'll talk about it in just a second. Although hydrogen is pretty much right there on most periodic tables, is actually not part of group 1. It just happens to be there. Group 1 really starts with lithium, which is below it. But group 1, group 2, we skip the middle part. Group 3, 4, 5, 6, 7. Most people just call it that, group 1, 2, 3, 4, 5, 6, 7. Most people don't call it group 1A, group 2A and stuff. They kind of drop the A, but technically that is what it is. As we go left to right on the periodic table, that is in a row. That is what is referred to as a period. And on the periodic table, there's like 7 periods, like 1, 2, 3, 4, 5, 6, and 7. And those would be heading obviously in that direction there. Also, we've talked about the number just a minute ago. That's on top of the element symbol, and that is the atomic number, which is obviously our number of protons. The periodic table is basically broken up into 3 sort of categories. On most periodic tables, you can see what is sometimes referred to as like a staircase. Kind of starts over here by boron and kind of works its way down. You can also see on that periodic table sort of highlighted a little darker, kind of coming down. To the left of that staircase, and also the 2 rows that are on the bottom, which are not pictured here, those are metals. To the upper right of the staircase, those are non-metals. And on the staircase are what are referred to as metalloids, or some people call them semi-metals. Metals are good conductors of heat and electricity. They can be hammered into sheets, kind of pulled into wires. Most metals have shiny appearance. For the most part, most metals are solids at room temperature, except for our friend mercury there, which is Hg, which is why mercury on a lot of periodic tables are a different color. It's kind of blue on a lot of periodic tables. It actually is a liquid. Non-metals, on the other hand, are kind of opposite in terms of obviously characteristics that we see in metals. They are sort of dull, they're brittle, they're used for insulation. They're also poor conductors of heat and electricity. And unlike metals, which are mostly solids at room temperature, non-metals can be a variety of states: solid, liquid, and gas. So you can see nitrogen, oxygen, chlorine are gases, bromine is the liquid, carbon and sulfur are solids. A lot of non-metals are those diatomic molecules we talked about. That they come as diatomic molecules, and they're still elements. That is why when we look at the periodic table over here, that is hydrogen. Hydrogen is actually what type of element? It is a non-metal, even though it's hanging out over there with the metals. Below it, which is lithium, is actually a metal. So hydrogen has a lot of unique sort of characteristics, and in a lot of cases, we treat hydrogen almost like it's working like a metal when it's bonding and stuff like that, and naming and things like that. But hydrogen is actually a non-metal, which again is why it's not really part of group 1. If you're old like me, they used to make periodic tables very commonly. They would put hydrogen actually on both sides, so you would see like hydrogen hanging out over here as well. Sometimes they don't do that too much anymore, but it technically is a non-metal. So you should keep that in mind. Hydrogen. The metalloids or semi-metals are coming down again, sort of as like 2s, if you will. So we got like silicone, GE, arsenic, and so forth coming down. Metalloids are pretty much elements that have properties that fall kind of on both sides of the staircase. So the same element will have some properties that are very similar to what we see with metal, and the same element will have some properties that are very similar to what we see with non-metals. It also does make sense about where they're located as we go from left to right: metals and then into non-metals. So these guys sort of bridge the gap between the two, and they have characteristics that are sort of similar on both sides of the staircase. Now, some groups do have special names that you do need to be aware of. The first group is group 1. And once again, as we just talked about, it does start with lithium here. So it is lithium, sodium, potassium. Those are what are referred to as the alkali metals. Right next door where we have beryllium, magnesium, all those good guys right there. Those are what are referred to as the alkaline earth metals. Going all the way over to group 7, which is over here. That's group 7. That is our fluorine, chlorine, bromine, iodine, all of our diatomic guys. Those are the halogens. And right next door at group 8, as we'll talk about here in just a second, are the noble gases. So you do need to know those. Group 1 and group 2, which is the alkali metals and the alkaline earth metals. Alkaline means basic. So a lot of strong bases come from group 1 and group 2 on the periodic table when they hook up with hydroxide OH minus. That's where we get things like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. So kind of coming this way. These guys with hydroxide make a lot of the strong bases that we very commonly see. So once again, a little bit about some of the halogens there, which we'll do an experiment next week, I think, involving some of them. But they are very reactive nonmetals. They react with metals to form ionic compounds, and they react with hydrogen to form acids, like HCl is hydrochloric acid, which we've used before. HBr is hydrobromic, and so forth. And like we talked about before, most of them are gases. Some are sort of like a liquid. And we used iodine, I think, the other week there in an experiment, kind of that purple color and all that good stuff that came out of it is our iodine. So a couple other things, like I said, group 8 all the way over here. That is our noble gases. Noble gases are sometimes referred to as rare gases. They are what are referred to as being chemically inert, which means they do not react with others. They'll react with themselves, but not really other people. As we'll talk about when we talk about bonding, that's essentially what everybody tries to achieve, is the same electron configuration as noble gases because it's really, really stable. The 2 rows on the bottom here are set aside so your periodic table is not super wide. Actually, this is the only school that I've ever seen put it on the wall correctly in the whole building, and it took up the entire wall. And that's because if you count the numbers here, the atomic numbers, that's 57, then 72, which means this guy actually goes right there. That's 89 below it to 104. That's 90, which means this guy actually goes right there. So these 2 rows technically gonna go into here. Then would obviously shift your periodic table off the cover of your book and all that good stuff. Between group 2 and group 3, and by the way, those are the lanthanides and actinides. Those are the 2 elements that they technically should follow on the periodic table. A lot of radioactive elements, man-made elements, all those guys with the nice names like californium, einsteinium, all those things are found down there. Good news is in this class, we don't deal too much with those 2 rows on the bottom. Like I said, if you go to 1B and do the nuclear chapter, you'll deal with obviously some of those guys down there. Between group 2 and group 3 on the periodic table, basically from here to here, between SC and zinc there and down, those are transition metals. So our transition metals, again, starting here to here and everybody underneath. Transition metals, one of the characteristics of transition metals are because they are metals, they lose electrons, but they have the ability to form multiple types of charges depending on the situation. So something like iron, for example, could make +2 or +3 charge depending on the situation. Copper could do +1, +2. So they have sort of a variable charge when they do getting charged. A reminder that anything from the periodic table that is uncombined by itself does not have a charge. So things only get charges when like a metal and a non-metal actually hook up. That's sort of when things get charges. But if you have any of these elements by themselves, they do not carry charges. The characteristic shape, obviously, of the periodic table place elements together that had similar physical and chemical properties. Elements in the same group have similar properties. And obviously, as you move from left to right, we are gradually changing from metals into non-metals as we go upwards to the right there. Any questions on the periodic table? So clearly, you know the periodic table, which way groups go, which way periods go, the numbering of 1, 2, 3, 4, 5, 6, 7, 8. You need to know where the alkaline metals are, the alkaline earth metals, halogens and noble gases are located. You need to know where the transition metals are located. And obviously you need to know what things are metals, non-metals, and metalloids, and obviously some characteristics of those. Any questions on any of that? Okay. So as I mentioned, noble gases are pretty much chemically inert. There are some noble metals like gold, silver, and platinum. They're virtually unreactive, and those are found in the transition metal region. And here's again just some characteristics of our noble gases, most of which we've talked about here along the way. As I mentioned before, our diatomic molecules are two atoms together, and obviously oxygen and hydrogen are two nonmetals that are diatomic. And here's the rest of those guys, which are our nonmetals. All right, we're going to kind of skip through that one, I think. So let's talk a little bit about ions here, and we'll talk more about it when we do talk about, obviously, naming. But atoms that is neutral have no charge. Like I mentioned before, when something does gain a charge, it is referred to as an ion. And ions are basically things that either gain or lose electrons, and that is when these things really do gain a charge. So if we look at something like sodium with 11 electrons, because it has 11 protons, when it is neutral, if sodium loses 1 electron, which is typically what happens with sodium, it becomes sodium with a +1 charge. And again, it goes from sodium with no charge that had 11 protons and 11 electrons to sodium with a +1 charge, which once again, the protons stay the same. Positive means we lost an electron and gives us a +1 overall charge. And again, that is a cation that occurs. Same thing if we look at something like magnesium. Neutral magnesium has an atomic number of 12, which means it has 12 protons and 12 electrons. Magnesium typically will lose 2 electrons. It's their outermost electrons. When they do, magnesium ends up with a +2 charge. And once again, as we talked about, it is just the electrons that are changing here. And a magnesium with no charge, 12 protons, 12 electrons, gives you 0 charge. Magnesium +2 charge, 12 protons, and now 10 electrons, gives you that +2 charge, which once again is where that +2 comes from. Aluminum as well will actually lose 3 electrons. So instead of 13 protons and 13 electrons in the neutral aluminum, aluminum with a +3 charge means that it has basically 10 electrons as well. And this is what I was talking about before. If you know aluminum's atomic number is 13, and you see aluminum with a +3 charge, the plus means that it lost electrons, and 3 is how many. So you basically just subtract 3 from that protons, and that will give you the correct number of electrons in this case. Cations, if we have the cation by itself, not attached to anything else, but you just have the form of something that is a cation that has a positive charge. The way we go about naming it is we simply just use the whole entire name. So our Na+ here, this would be the sodium ion, just the whole name of it. We put ion at the end because it has a charge. This guy here, the whole name of that element is magnesium, so that would be the magnesium ion. And this guy here that has a charge, the whole name of that guy is aluminum, and that would be the aluminum ion. So if you're ever asked what is the name of a cation by itself, and you have the formula for it, it's pretty simple. It's just the element name, and you just put ion at the end because it has a charge associated with it. Any questions on that there? The one thing that it also works for is even a non-metal like hydrogen, which is kind of the only one that will do a positive guy. That would be the hydrogen ion. So pretty much anything with a positive charge, whole name of the element, add ion to the end. And that's the way we kind of name those guys. Anions are a little bit different in the sense of what is happening and also sort of how we name them. Anions, as we talked about, basically are negatively charged ions. They are results from gaining electrons. So something like chlorine, which is in its neutral state, has an atomic number of 17, which means it has 17 protons and 17 electrons, gives it no charge. Chlorine will make a -1 charge. It still has to have 17 protons because it's chlorine. -1 means negative it gained, and 1 means it gained 1 electron. So we add 1 electron there to our atomic number, and that gives us 18 electrons, giving us a -1 charge basically left over. Same thing with something like oxygen. Oxygen is 8, which means it has 8 protons and would have 8 electrons in a neutral. Oxygen makes a -2 charge. So once again, because it is still oxygen, it has to have the same number of protons. But in this case, it will have 10 electrons, 2 more than it started with, gives you the -2 left over, and where the charge comes from as well. Any questions on that there? Now, the way that we actually name anions is we drop the last part of the name and we add IDE to it. So when we take something like chlorine, we drop the last part, it becomes the chloride ion. If we had fluorine that had a charge, like this guy, F-, we drop the last part of fluorine and we put the IDE there, and it becomes the fluoride ion. Oxygen, we drop the last part and it becomes the oxide ion, IDE. So OXIDE for this guy here. So any ion that is negatively charged, that's pretty much how you go about naming it. Drop the last part and put IDE at the end of it. Any questions on that there? This is also how we sometimes represent what's happening. Chlorine gains an electron, ends up with a -1 charge on the other side. The electron is on the reactant side, like it's being gained. We looked at sodium, which I kind of went over the equation there, but we'll do that here. Sodium becomes sodium with a +1 charge, and it's like it's losing an electron, and it'll be on the product side. So if you had to sort of write a little equation to represent it either gaining or losing electrons, electrons will be on the reactive side or the left-hand side of the arrow. In a case where it becomes negatively charged and an anion is formed, the electrons will be on the right-hand side of the arrow. When it loses electrons, like it's being given off or sort of lost on the right-hand side of the arrow. Any questions on that there? So as I mentioned, not everybody will have a charge if they're by themselves, but when things do form charges, there are certain things that have fixed charges, and you should be aware of that. So pretty much everybody here in group 1 will form a +1 charge. Everybody in group 2 will form a +2 charge. Everybody in group 3, for the most part, that's aluminum, will form a +3 charge when it does. This is sort of where the staircase kind of comes through. So we skip 4, we go to 5, and that's where we have like our nitrogen and phosphorus. These guys will form a -3 charge. As you can see there in group 6, -2, group 7, -1. So these are guys that have fixed charges no matter what the situation is. If they make a charge, that is the charge that they make, no matter who they're attached to. They're a little bit different, as I mentioned. They can form a variable types of charges. There are 3 exceptions, though, and that is zinc and cadmium. These guys, when they form charges, will always form +2. And then if you hang a left there by cadmium to silver, that guy will always form a +1 charge. So those are sort of 3 exceptions in the transition metal region that if they form charges, they actually have fixed charges. These sort of 3 guys, zinc and cadmium will always be +2 and silver will be +1. Any questions on that there? That's definitely something good to know as we get into naming coming up very shortly, and charges and putting compounds together. Speaking of compounds, ions, most common pure substances are poor conductors of electricity, but some substances, when they do dissolve in water, for example, they basically become electrolytes, and electrolytes conduct electricity really well. The reason electrolytes conduct electricity really well is the presence of these charged ions floating around in the solution. So you got the solution that has the charged ions that are floating around in it, and that's what sort of helps complete everything, if you will, and conducts electricity really, really well. Pure water is actually a very bad conductor of electricity because pure water has no ions in it if it's pure water. So there's no ions to help conduct electricity. Let me be very clear, the water coming out of your pipe is not pure water, so you will get electrocuted, right? They actually put ions in the water to purify it and stuff like that. So don't do anything like blow dry your hair in the shower because you will get electrocuted. But if you have just technically straight H2O, nothing else in there, it's actually a really bad conductor of electricity. So there's a few different types of electrolytes. There are strong electrolytes, which 100% break apart into ions. Like sodium chloride solution. A sodium chloride solution is actually basically 100% sodium ions, and chloride ions is really what you have in that solution. You have none of these sodium chloride units still together. And because of that, it conducts electricity really, really well. If you put a light bulb with some electrodes on it, it would come off and be very bright. Really good conductor. There's also weak electrolytes, which mainly stay together. But break apart a little bit into ions. Like, for example, hydrofluoric acid. It is a weak electrolyte. It will break apart into H+ and F-. This is mainly what you have in solution, but you have a little bit of these guys here. So because it's still able to produce a little bit of ions floating around in the solution, it will still be able to conduct electricity, but it won't be able to conduct electricity anywhere near a strong electrolyte. So in terms of a light bulb sort of example, strong electrolyte, light bulb, super bright. Weak electrolyte, when the light bulb would go on, it'd be really, really dim. So it's still able to sort of conduct electricity, but again, nowhere near what a strong electrolyte could do. And you can usually recognize a weak electrolyte by the arrows. There's usually arrows heading in both directions versus a strong electrolyte where the arrow's heading in one direction. Arrows heading in both directions means this is a reversible reaction, which means there's a forward direction going from left to right And then at some point, these guys on the right-hand side will come back the other way and make what's on the left-hand side there. So what ends up happening is you get the reaction sort of happening in both directions simultaneously. It will eventually come to what's known as chemical equilibrium, and you'll have a little bit of reactants, you'll have some products present at that time. Last type of electrolyte is actually a non-electrolyte. They will dissolve but produce no ions. So because they will produce no ions, they will not conduct electricity. So the difference between the three: strong electrolyte 100% breaks apart into ions. That's all you got in there. Conduct electricity really well. Weak electrolyte mainly stays together, but still able to produce a little bit of ions. So still able to conduct electricity, less than obviously a strong electrolyte. A non-electrolyte will dissolve in solution, but because there's no ions present, will not conduct electricity. Example of that is we take sugar. Sugar dissolves in water. Sugar is a molecular compound made up of carbons, hydrogens, and oxygens. There's no ions present, but it will still dissolve. But again, because of the lack of ions, we will not get anything conducting electricity. Any questions on that there? And there's sort of an example behind there of the light bulb I wrote all over. All right. Now, whenever a compound forms between a metal and a non-metal, and once again, it is the metal that always makes the cation, which is our positively charged ion. And it's always the non-metal, which makes our anion, which is the negatively charged one. And by the way, what happens is basically it is the metal that transfers electrons to the non-metal. We make an ionic compound as a result of that. When we put the ions together in the formula for an ionic compound, it should always equal 0, the actual formula for it. So when we take something like our sodium ion and our chloride ion, +1, -1, when we put them together, gives us no overall charge. If we take something like Ca, which makes a +2 charge, and F-, when we put them together to make our formula of calcium fluoride, if I put them together as one of each, will my charges cancel out? They will not, right? We'll have +2 and -1. We actually need one more of the negative guy. That gives us a grand total of -2 and +2. Now, when we put it together, CaF2 would be the proper formula here. So when we take a cation and anion, put them together in their formula, the overall formula should have an overall charge of 0. And it also should be the simplest way you could get to 0. So the simplest way to get to 0 is how the formula should be. Obviously, we could do like 2 calciums and 4 fluorides will get us to 0, but we want the simplest way to get to 0 with whole numbers. And the formula for the compound will never have charges written, but it is still made up of 2 things that obviously have charges associated with them. So again, the cation here would have a +2 charge, the anion would be a -1, and we would need 2 of them. So if you're asked to write the formula for something that has a charge that's an ion, it should include the charge when you write the formula. If you're asked to write the formula for an ionic compound which puts 2 ions together, when you do that, you need to do it so we end up with no charge. Any questions on that there? So again, let's take a look at a couple of these examples here and see how we get to our formulas. If we put together barium, which has a +2 charge, and oxygen, which has a -2 charge, we just need one of each. So that is why the formula there is BaO. Once again, that formula has no overall charge. but is made up of two things with charges. When I look at aluminum, which is +3, and sulfur, which is -2 or sulfide, when I put them together, the easy way to figure it out is 3 times 2 is 6. So 6 is sort of our common number. So to get my aluminum to 6, I need 1 and 2 of these guys, gives me +6. To get my sulfide to 6, I need 1, 2, and 3 of these guys, gets me to -6. +6 minus 6 equals 0. So that is why the formula here would be Al2, because there's 1 and 2, and S3 because there's 1, 2, and 3 of them necessary to get us to that formula. Question on that there. Lastly, here we have potassium, which has a +1 charge, and phosphide, which has a -3 charge. And in this case, we actually need 3 of the potassiums to balance it out, right? 3 positive charges to balance out the -3 charge. And that's reflected here in our formula, K3P. That means we have 3 of these potassiums, each at +1, and 1 phosphorus at -3. So when we look at that formula of K3P, tells us 1, 2, 3 of these guys +3, and 1 of these guys at -3. Once again, equaling 0 when it balances out. In terms of the name, when we would put the names together, in this case, this would be barium oxide, IDE. This would be aluminum sulfide, IDE. Potassium phosphide, IDE at the end of it, would be the name of those guys. Question on putting them together. We'll talk more about it when we get to naming officially. Sometimes people say just do the crossover move with the charge, and that will get you the right number on the bottom, and it will work like 90-ish% of the time. It will not work 100% of the time. So you shouldn't just blindly cross them over unless you're okay with 93, 4% of the time. Any questions on that there? Okay, I think that wraps up chapter 4. All right, we're going to continue on to chapter 11 for a little bit. Okay, so we are off to chapter 11 here. We're going to really talk about electrons for the most part, electron configuration, and we'll talk a little bit about periodic trends towards the end here. So as we talked about, Rutherford basically described the atom as being or having a positive core, which is the nucleus, with our negatively charged electrons really moving about from it. Again, as we talked about, there is an attractive force between the electrons, which are negatively charged, and the nucleus, which is positively charged. Again, kind of holding it there so they can't completely sort of escape. As we'll talk about in this chapter, as we mentioned before, really electrons are moving in a pretty random pattern about the nucleus. And again, as we know more about sort of how it's moving and less about sort of the speed at which it's moving, we learn little about each of those things. And that's what's known as the Heisenberg uncertainty principle, that, if I know more about how fast it's moving, I know less about where it's at, its location, and sort of vice versa. A lot of sort of modern ideas here in terms of electrons and what happens as electrons sort of transition from one energy level to the next was done by a guy named Planck. He did a lot of work with radiation. And basically, Planck's work showed that energy can be released in only certain definite amounts, which he sort of referred to as a quanta of sort of energy. And the idea here is about radiation is we get really the emission and transmission of sort of energy as it moves through space, really in the form of waves. So the idea of quantized energy is really this idea that for our purposes here, as electrons transition from one energy level to the next, either a lower energy level to a higher energy level or a higher energy level to a lower energy level, they will be able to gain or lose enough energy to make that transition. So sometimes people, I think we'll see a picture of this a little bit later on as well, think of sort of quantized energy like if you're walking up steps, right? If you find yourself walking upstairs or even downstairs, I suppose, you have enough energy to get yourself to one step, right? And then you have enough energy to get yourself to the next step, right? So you either get yourself to this step or this step. You don't usually decide like halfway up the step, I'm just going to lay it up here. I don't feel good about it because you're going to fall. And sort of as electrons sort of transition and they lose and gain energy, they will lose enough energy or gain enough energy to make it sort of a full transition from one energy level to the next. They won't find themselves sort of in between energy levels or anything like that. As they do this, they either got to absorb energy in the form of a wave or photon of light, or they have to release the energy in the form of a wave. So we should talk about some of the important properties of a wave. A wave can be thought of as a vibrating disturbance by which energy is transmitted. The speed of the wave depends on obviously the wave and where it's going. The wave is actually moving past our bird here as he's relaxing, right? And he's going up and down as the wave kind of goes through. If you've been in the ocean and been hit by a wave, you know it has pretty much a lot of energy, right? And all that good stuff. So a lot of energy through space is transferred as waves. Seems like a good day to go to the beach. I don't know. So some important parts of the wave. Let's talk about those guys. First off, it is the wavelength. The wavelength is sometimes abbreviated with the lambda symbol, and that is the distance between basically 2 points on a wave. So if you have a wave that's kind of rolling, our wavelength of my really badly drawn wave would be somewhere like there, or it could be the troughs there, would be my wavelength as we go through it. In terms of units for waves, meters are very common, centimeters and nanometers. So a reminder, a couple of these things, right? There's 100 centimeters in 1 meter. If I get that. And 1 nanometer, there is 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters. So those are very common conversions that we use a lot with waves. A lot of visible light is given in nanometers, like where we see colors, red, orange, yellow, green, blue, indigo, violet. Frequency, which is a lot of people call it a V, but it's not really a V, it's a nu. And that is basically the number of ways to pass a particular point in a given second. The units of frequency are a hertz, and a hertz is also a reciprocal second, which is that, or basically that. A hertz is the same as a reciprocal second, so they are a one-to-one relationship. We also sometimes with frequency use mega, right, which is 10 to the 6. Like when you dial your radio into 95.5 megahertz, right? That's the frequency of your radio waves coming in to your radio. The amplitude is the vertical distance from the midline to the peak or trough of a particular wave. So amplitude would be there. We could calculate the speed of a wave by taking basically the wavelength times the frequency, and that usually will give us the speed of the wave in meters per second, as wavelength is usually units of meters. Frequency is 1/seconds. So a very common sort of speed of a wave is given in meters per second in terms of the units. Any questions on any of those things there? So here we get some of the prettier pictures here of our waves. Now, like waves like electromagnetic radiation, which is basically the emission of energy in the form of electromagnetic waves. Electromagnetic radiation can sometimes have properties, very characteristics of particles. So one thing that sort of discovered through experiments is the idea that was sometimes referred to as the dual nature of light. Particles can basically behave like particles. So particles like electrons, for example, but particles could also have sort of wave-like function as well. So they could behave like waves, and vice versa. Waves can have particle-like functions as well. So both particles and waves can basically kind of behave like each other and have functions that are similar to each of one another. So sometimes it's referred to as the wave particle nature of light or the dual nature of light when we talk about it. One could think of a beam of light as basically traveling through space as a packet of energy, which are sometimes referred to as a photon. There is a relationship between wavelength, frequency, and energy as a wave is moving through space. And that basically is this: the longer the wavelength, so the longer the wavelength, the lower the frequency, the lower the energy associated with it, as opposed to a wave such as this, which has a shorter wavelength, a higher frequency, and usually is higher in energy. So as particles, for example, like electrons, either transition upwards in energy from lower energy to higher energy, or downward from higher to lower energy, the wavelength and the frequency of that photon of light that comes off that allows them to do those transitions will result in a certain amount of energy associated with them as they're moving through space. And again, typically the shorter the wavelength, the higher the energy, and the longer the wavelength, the lower the energy. So for example, as we will see, speaking of radios has a longer wavelength, so kind of lower in energy, which is why it's not too bad for us to listen to the radio as we're driving around in our cars. Something like X-rays has a very short wavelength, which has very high energy, which again is why they throw a lead vest on you and leave the room when they shoot the X-rays, right? Because it's very high energy, and we don't get X-rays every day of our life and things like that. So here you can see light as a wave, having some wave function, and it could also be thought of as sort of a stream of photons that carry sort of this packet of energy as it goes through. Even things like color have a difference in terms of energy. Up on top there is red. That's the red wavelength. On the bottom is more of the bluish wavelength. And we can see blue actually has a much shorter wavelength, and it's actually higher in energy than red, which has a longer wavelength and lower in energy. So even with colors, kind of on the red side of the color spectrum, if you will, is sort of our lower energy colors. And as you head to blue and violet and purple on that side, is a shorter wavelength, a much higher in energy associated with those colors. So one feature that is common to all electromagnetic radiation is the speed at which they travel, and it's 3 times 10 to the 8 meters per second, or about 186,000 miles per second. That is what is known as the speed of light. So that is a constant. The speed of light is 3 times 10 to the 8 meters per second. You could calculate the wavelength or the frequency by using this formula. This is the speed of light, which is this number, is equal to the wavelength in meters times the frequency in reciprocal seconds. So if you wanted to calculate the wavelength, it would be the speed of light divided by the frequency. If you wanted to calculate the frequency, it would be the speed of light divided by the wavelength. So for example, if we had say 4.68 times 10 to the minus 7 meters as our wavelength. We want to know the frequency that would come from that. We can basically use this equation right here and take that. The frequency would be 3 times 10 to the 8 meters per second divided by 4.68 times 10 to the minus 7 meters. In this case, the meters and the meters will actually cancel each other out. We definitely would want to use our exponent button here, 3 exponent 8 divided by 4.68 exponent minus 7. Going to give us, not that, going to give us, I'm just going to go to the top here and write it, 6.41 times 10 to the 14. Once again, the units are actually 1/seconds, and that would be the frequency associated with a wavelength of light that has that wavelength. So what we can calculate here, and as we'll talk about next time as well, we can calculate also the energy that's associated with that wavelength of light. The idea is something like electrons, as they are transferring from one energy level to the next, is if they are going from a lower energy level to a higher energy level, they have to gain a certain amount of energy to do so. And if they go from that higher energy level back to the lower energy level, they have to give off that amount of energy in the form of a wavelength of light. It's the idea of sort of conservation of energy. So there's going to be a certain amount of energy coming from the surroundings to the atom to allow the electrons to go up in energy. But as they come back down, the atom will then release the same amount of energy required for those electrons to transition down to a lower state of energy. Any questions on any of that there? All right, we'll lay it up there for today.